treat for you this afternoon. Two speakers, experts in their field, Laurence Chèze and Claudia Mazzà, and they've been allocated the keynote lecture on measurement technology. So, without further ado, I invite Laurence to the stage.
Thank you for introduction. So, Claudia Mazzà from the University of Sheffield and myself from the University of Lyon are very delighted to present you today the evolution from the past to the present and then the future perspective of the measurement technologies. First, I will be in charge from the past to the present devices, and I will hand with the limitations of today's technologies, and then Claudia will present you the avenues in order to improve the movement analysis. So, interest in motion emerged long ago, but without going back too far, I wanted to spot two pioneers of the 19th century. The first one is Edward Muybridge, who was an English photographer, very renowned for his photographic studies about motions. And for example, he shot a horse crossing wires attached to multiple cameras, because until this time, it was thought that there is no time when all the feet of a horse left the ground. He developed the proxyscope, which can be seen as the first movie projector. At the same time, Jules-Étienne Marey, who was studying medicine in France and who loves mechanics, developed also multiple scientific devices in order to collect movement either of human beings or animals. And for example, with the chronophotograph here, you can see that he was able to first quantify the plane kinematics. Again, Jules-Étienne Marey developed the experimental shoe. Inside the sole, there is an air chamber in order to detect the foot hitting the ground. And the first force platform able to record the vertical and the shear components of the ground reaction. It was a purely mechanical device and was developed by Herbert Elfman. So all these technologies can be categorized in three groups. The first one are the devices which are designed to measure the movement. In the other group, the devices to measure the causes of the movement, that is to say the forces, and then devices to make the link between the movement and the anatomical structures. So let's first focus on the movement analysis, movement measurement technologies. In 190,050 appeared electrogoniometers. Then 55 years later, active marker systems, then passive marker systems, magnetic system, and 5 years ago only, new devices based on structured light cameras. Let us explain briefly how they work. Electrogoniometers, a device that converts joint angle to a voltage based on either potentiometers or strain gauges. Each extremity is firmly attached to adjacent segment and should be aligned to its principal axis. The advantages of such devices is that they give the direct output of the joint angle with quite a high sampling rate, and they are low cost. But the drawbacks are the time consuming to fit and align correctly the device on the segment. They are sensitive to out-of-plane rotation, and joints are not moving like a hinge joint. The accuracy is average, and if you use many of these devices, you can have many straps and cables which disturb the movement of the subject. The main application using this kind of device used to assess the range of motion of one single joint, mainly in physical therapy studies. Then, active marker systems typically use 3 photosensitive cells arranged on the same pre-calibrated unit. Each sensor emits an infrared signal. The LEDs are triggered sequentially to allow automatic identification of each sensor, and then the synthesis of 3D coordinates is done by triangulation. Here the pro are automatic identification of the sensor, and no calibration is required at all. They can collect data in quite important capture volume, and the accuracy is very good. But wire connections are required to power sensor and can disturb the measurement. The sampling frequency is limited if we follow a very important number of sensors because of the multiplexing of the signal in time, and they are high costs. They are essentially used to assess details in movement realization, for example, in motor control and neurosciences application. The passive marker systems used light-emitting diodes ring surrounding the camera lenses, which emits stroboscopic radiation. The markers are plastic balls coated with a retroreflective material which reflects the light in incident direction. A filter and the camera's threshold should be adjusted to only the bright reflective markers are sampled. And then again, the synthesis of 3D coordinates is done by triangulation using at least 2 cameras based on the epipolar geometry, which allow to detect easily homologous points on distant cameras. The advantages of such systems are here the subject is free to move without wire. The sampling frequency is quite high and does not depend on the number of markers. The accuracy is quite good. Nevertheless, the marker identification is not fully automatic. If occlusions or swapping appear in the trajectories, then a post-processing is required. Again, a calibration step is required before data collect, and they are high cost. They are the most widely used systems, especially in gait analysis and when whole body movement has to be collected. Magnetic systems, a transmitter generally composed of 3 electric wire coils at perpendicular axes, generates a 3D low-frequency electromagnetic field. The sensors also are consisting of 3 orthogonal detection coils and are fixed on the subject and detect the relative strength of the magnetic field. Then the calculation of the differences in potential between each sensor and the antenna provides both its position and orientation. The advantages here again, automatic identification of sensor, no calibration is required in this kind of system, and the accuracy is good. But wire connections from sensor to power them, the size capture volume is quite limited with such systems, and the measurement is sensitive to meter. The cost is about medium. The main application of this kind of systems is in rehabilitation and virtual reality. Then, more recently appeared systems based on structured light cameras. Here, a video camera is used to acquire a 2D image of the scene under a structured light illumination. When the surface is non-planar, the geometric shape of the surface distorts the projected structured light pattern as seen from the camera. Then, the projector camera system being previously calibrated, the 3D surface shape is extracted from this distortion. These small devices are very low cost, but they are sensitive to daylight. You can collect data only on quite limited range and at low frame rate. And moreover, if you want to assess joint kinematics or body kinematics, you need a predefined simple body model, resulting in quite low accuracy. But despite of this low accuracy, many applications arise in rehabilitation through virtual reality games, even at home. Now let us speak about the forces devices. Again, from the past, the first one is the electromyography, which has been developed in, again, 1950. And then the force platform, about 15 years after. Here I want to quote Professor John Paul from the University of Strathclyde. I had the chance and the opportunity to meet him during a European project that we were involved in about 20 years ago. And he was the first scientist, one of the first scientists who used force platform in order to measure the joint loading in gait. Then the isokinetic dynamometers appear, and then the pressure distribution platforms. How electromyography works: when a muscle fiber becomes innervated, sodium ions flow into muscle cell membranes, resulting in a depolarization. When a threshold is exceeded, an action potential is developed, and the process travels along the muscle fiber. The differential amplifier receives a bipolar signal corresponding to the difference of potential between the two electrodes. The limits of these systems is that they require proper skin preparation to minimize skin impedance. The crosstalk can appear from neighboring muscles. The more important is that no direct relation exists between the activity measured and the force in the muscle, and only superficial muscle can be assessed, at least if we use superficial surface electrodes, and movement artifacts can perturb the measurement. The force platform is based on two rigid plates. Between each, transducers are located. When a load is applied to a transducer, either strains occur in the supporting cylinders. This changes the electrical resistance of the strain gauge and produces a change in the voltage, or an electrical charge results in the piezoelectric crystal. But in both cases, the electrical response is proportional to the force being applied. 3D transducers are located at each corner of the platform, and the combination of all these measurements is reduced to a resultant force and a resultant moment at the center of the platform, or the center of pressure and the free torque. The limits of the force platforms are that sensitivity and measurement range should be adapted to each application targeted. A good dynamic response is essential, and natural frequency should be much higher than event frequency. Again, crosstalk can happen. The size of the platform should be adapted to each application, and a rigid mounting on the ground to avoid external vibrations with a flow level to avoid targeting of the plates are necessary. Isokinetic dynamometers concept consists in controlling a joint constant speed with accommodating resistance to the net moment developed by the muscles crossing the joint. The muscular force varies at different joint angles because of different biomechanical properties of the musculoskeletal system. So the accommodation of resistance is the only way to allow for muscular loading, maximal muscle loading, through the entire range of motion. The limits is that you need to correct gravitational effects with this kind of devices. You can only interpret the constant velocity period because of inertial artifacts, and you cannot evaluate a single muscle because of antagonists' muscles activity. Moreover, artifact can appear due to a misalignment of the joint and the device axis of rotation. At last, pressure distribution mats, it consists in a rigid or a soft array of pressure sensing elements arranged in a matrix configuration. These sensors are either capacitive, resistive, or piezoelectric, and they measure a force. Then the systems provides a dynamic map of the local pressure, which is the perpendicular force per unit area, and gives also center of pressure displacements and so on. The limits here are you cannot measure shear forces with this kind of mat, and for soft mats, the direction of the measurement axis can vary. The resolution, the pressure range, and the threshold should be adapted to each targeted application. And sometimes you can have a displacement between the map and the ground, or here the back of the horse, if you test a saddle. The sampling frequency is quite limited also. So, what are the open issues using the present technologies? The first one is that all these technologies are designed to follow the external envelope of the segments. And what we need is the joint kinematics, that is to say, the internal skeletal movements. The relative displacement between external markers and internal bone are the so-called soft tissue artifacts and are still an open issue. Many studies have been realized in order to assess these artifacts. They are based on quite invasive protocols, either using intracortical pins or fluoroscopy 3D registration. And a lot of studies also show that there is a substantial influence of these soft tissue artifacts on joint kinematics. For example, here, the study of Stagny showed that for the knee joint kinematics, the error can reach 50 to 100% on abduction-adduction or internal-external rotation of the knee, while stereoscent or sit-to-stand tasks. So it's quite important. Moreover, if you combine movement measurement and force measurement, then you could quite easily calculate the net joint moments using inverse dynamics method. But if you want to assess the joint reaction forces, then you need a further step, and you need to evaluate the force in each of the muscles. Finally, all these devices are designed to accurately measure the movement in a controlled area of a lab. But in the near future, if we want to assess daily activities in situ, will it be possible? I will ask Claudia to try answer these questions.
So, good afternoon. Thanks, Laurence, for leaving me with the most difficult questions in the most difficult time ever. So, as we have seen from the previous presentations, this is like what we normally obtain using marker-based motion capture analysis and as associated with the measurement of ground reactions within a clinical gait analysis laboratory. Normally, we represent the information that we obtain, that is describing the movement of our skeleton, through a description of the joint rotations, the joint moments, of the activity of the muscles. And this can be done to solve a number of problems and a number of clinical questions. Normally, the most common approach is that of looking at the time pattern of the different curves under different conditions. In this case, in this example, the different curves on the slide simply represent the effect of gait speed in terms of the estimate of the joint rotation. Normally, the anatomy that we use in order to get this information is obtained by palpating a few points on the subject's skin and then scaling a generic skeleton to the size of the subject that we are observing. There are certain applications for this. Is certainly something that is not informative enough. If we want to know what happens when we have serious deformities in a bone, even within the two limbs of the same patient, this generic scaling of the anatomy might not be enough. And even more, if we want to try to explain what different muscles activations and different movements would cause in terms of progression of a pathology or prediction of an intervention, we need to get into more details. We need to move on from joint moments to muscle and joint forces. This is a very nice paper from the group in Bologna, the Rizzoli Institute, which shows one that is probably the most common trend in trying to define patient-specific musculoskeletal models. The way to do it is to join bone shapes and muscle paths as extracted from MRI imaging techniques together with our data recorded in the gait analysis laboratory by using markers visible in both modalities in order to register the two information and obtain a full model of the anatomy of the subject that we are interested in investigating. Once we have these data, these models prepared, we can then use software such as, for example, OpenSim in order to try to estimate the muscle forces and the joint contact forces. The advantage of using this patient-specific approach has been discussed by different papers. This is a paper from the group in Leuven, where they showed how using MRI-based anatomical calibration, it's actually possible to obtain more reliable data, for example, for the description of the joint kinematics of children with cerebral palsy. The next step, of course, would be that of trying to understand how much these changes and this variation in the description of the kinematics would actually affect also the estimate of the joint forces, for example. This is some results of some patient-specific modeling performed on 3 children with juvenile idiopathic arthritis, where the results of what can be obtained using a marker-based approach as opposed to an MRI-based approach can actually cause incredible differences in the estimate of the forces. Of course, we don't have instrumented ankles at the moment to try to see where the right answer is, but the message here is that we still need to be quite careful when looking at these different definitions and different way of doing things. An interesting development in the technology that would hopefully allow us to get even better results and even better personalization of our models is the use of dynamic MRI. In the last few years, there have been incredible results based on these techniques, which showed how it is possible to obtain information not only, of course, about the bone and muscles behavior, but also about the bone cartilage, the loads on the bone cartilage within a joint, for example. This is a study where they showed how it is possible to obtain 3D kinematics of the tibiofemoral joint based on this type of information. So, of course, this would be, this is where technology could possibly help us in the future. The real problem that we have when we try to merge this different information is that most of the time we get our data under, for example, in supine position, whereas if we want to have the best anatomical information to be fitted with our gait analysis data, this is where we should go. We should be able to get our anatomy description while possibly while standing, for example. The EOS system is a system based on very low dose X-ray, which allows us to get from two simultaneous images the possibility to reconstruct, for example, the 3D shape of the spine under load condition. Unfortunately, as the company says in their disclaimer, the current models are not able to provide us very detailed information about possible bone alterations or significant geometric alterations. So this might be an interesting way to go, but probably we are not there yet. So CT-based models, if we are interested in the bone, are really the best way, possibly the best way at the moment. This is an example of how clear, how defined could be a model of the bone, of the joint bones be reconstructed by using CT-based information. Of course, the problem we have here is that the radiation dose is typically quite high. So this is something that makes sense if our patients are getting a scan anyway for other reasons, and which is normally the case, for example, in knee pathologies. The other limitation is that we can't really see the insertions of the ligaments, for example, on a CT scan. For this reason, this is which is an information that when we personalize our model is certainly essential. However, there are techniques that can be used to overcome this limit. For example, here you see on a bone shape as obtained from a CT scan, we palpated a series of reference bony landmarks that can be easily detected. We can then use some anatomical reference data existing in the literature in order to build what can be called as a registration atlas. And on this atlas, based on different data sources, we can palpate virtually not only the same points that we have in this initial condition, but also the red point that you see here, which represents the actual ligaments origin and insertions. If we then register this information by using some shape registration techniques, we can obtain an estimate also of those points, those initial points, on our CT scan. We applied this method to a number of, in this case was 7 knees from patients with advanced osteoarthritis. They all went for knee replacement right after the images were taken. So, meaning that their bone shapes were really altered from what would be a regular anatomy. And you can see that we were able to obtain results that were absolutely comparable with those obtained directly from the MRI images, which is the best way to get this information unless you want to dissect your knee. And of course, this same concept, this same methodology might be applied also to other joints in order to further apply this concept. Again, we are not only interested in static information. When we try to build our models, dynamic conditions are really the way to go. This is an example of how a bone, and I thank our colleague in Bologna for providing these images. It's possible using dynamic fluoroscopy-based approach to reconstruct the movement of a knee that is modeled with very high resolution during a quite wide range of flexion extension. Again, this is a technique that requires quite much there is quite much radiation involved. So again, it's something to use with care. And is also is still limited to one joint at a time. So I hope I convince you that there is a way to go. But of course, if we want to build our models and use all this personalized modeling approach, the problem that we need to solve at the moment is that of having a full automated processing on the images, because at this point in time, building one of these models still requires too much time and is still too much operator dependent. But it's definitely something that we can expect to see developing quite significantly in the near future. The other problem that we have with this approach is that we must not forget that if we have rubbish data in input, we will have rubbish data as an output. Soft tissue artifact is the main problem. We heard this yesterday in Professor Capozzo's presentation, and Laurence showed it to us a few minutes ago. There have been a number of attempts and a number of studies which so far defined some model of the artifact that we could think of exploiting in our personalized modeling approach. We tried to see what could be the effect at the moment using these models that are available in the literature. We took a set of markers, just a standard set of markers, and we corrupted them using the models of the artifact that we could find in the literature at this stage. And we use these models in order to generate a descriptive statistics of possible joint kinematics that we could obtain as a result. We then fed these descriptive statistics of the kinematics to an OpenSim model, and we looked at the effect on the joint reaction forces. And as you can see, despite the fact that there are some compensation techniques implemented in the whole chain, these don't seem to be enough, especially if you look at the hip, at the estimate of the hip joint force. We still have variations that are possibly hiding the real information that we are after. So I think that together with developing better imaging tools, we should also keep developing better soft tissue model artifacts to be embedded in our modeling software if we want to really exploit the maximum out of these tools. So this is what we could do if when we are interested in a very detailed joint analysis and the estimate of patient-specific joint loads. There is also another side of the story, which is that for certain pathologies, like for example in pathologies involving elderly individuals, like osteoporosis, the interest might be in that of trying to understand whether a patient is a risk of fall, and if a fall could actually cause then a fracture that we could observe later on. For this reason, of course, the real way to go and to try to solve this problem is that of leaving the lab. Wearable sensors are available for any purpose and almost any reason at the moment. They are the tools that would allow us to quantify movements in their ecological environment and possibly also to quantify an individual lifestyle, no matter if it's a penguin or an elderly person. The principle, this is like the most common version of these sensors is the one that includes accelerometers, gyroscopes, and magnetometers. The information of these sensors is normally fused together in order to obtain, in every instant of time, the orientation in space of the sensor itself. This is it's not a trivial job. Obtaining this estimation is highly dependent on the algorithms used for the sensor data fusion, the movements that are observed, the disturbances in the environment. And there have been all range of errors that have been reported in the literature. So it's something that we can do, but we need to be careful here as well. This is just an example of how these sensors are used within a clinical environment. Normally, what happens is that they are located on the subject while the subject is asked to perform some predefined tests, like in this case is a time up and go, which is a very common clinical test. And what we try to do, starting from this information, is to discriminate the different phases of the movement and possibly also obtain some information about the joint kinematics while the patient is performing the movement. The detection of events based on signals coming from gyroscopes or accelerometers is something that can be extremely difficult. There have been different methods that have been proposed, for example, for estimating the different steps and the different phases of the step. And I think it's safe to say that at this point, this is something that can be accurately done in healthy individuals, no matter if you have your sensors on the ankles or on the pelvis. But when we go to patients, this is what we face. Each patient has a different pattern of signals, and we cannot think of reusing the same algorithms when we have to process something that is so different. So again, whereas we are there on one hand, on the other hand, the translation to clinics of all the methodologies is still undergoing, and it's hopefully something that we will manage to solve in the near future. Estimating joint kinematics using these sensors. Again, what has been done in the literature has been somehow replicating what's done for the motion capture-based systems. There have been methods that have been proposed based on a functional approach, where we ask our subjects to perform a series of known tasks in order to define the joint axis. There are other methods that have been based on imposing joint constraint, such as in the multi-body optimization. And here, we can obtain very good results using these methods, but the problem is that they only work with joints that have less than 2 degrees of freedom. And last but not least, there has been some attempt to replicate what's done also with the calibration, the direct anatomical calibration based on the palpation at some point, again, with quite accurate results. And in this case, the problem is that of the need of using additional devices in order to perform this anatomical calibration. So the point here, the good news is that no matter which of these approach you prefer, it is actually feasible to estimate joint kinematics using these sensors. But again, we must not forget that each of those, the estimate of the orientation of each of those boxes is still an issue. So if we have 10 degrees of error in estimating the orientation, that would cause the same errors in the joint kinematics estimate. Last thing that we might be interested in doing with wearable sensors is that of quantifying the physical activity and possibly even the sub motion that are performed during daily life. This is just a little sample of the huge variety of sensors that are available nowadays to solve this problem. The main differences between these sensors is in terms of the number of the differences between these devices is in the number of sensors that they include. So they don't measure only movement, but typically they can have also some measurements of physiological parameters such as heart rate or temperature. And of course, the more sensors we combine, the better we could expect our estimate to be. But at the same time, the difficulty and the prices of the sensors will change. There have been some interesting development based where these sensors have been even implanted under the skin. However, the accuracy once again can be an issue. This is a study that we did very recently, where we basically put us in the easiest scenarios possible. So we just used healthy individuals. We asked them to walk while wearing 7 different sensors, varying for the technology that they entail. And we then used some gold standard. We used some MIMUs on the ankles as a gold standard. And we asked our patients to walk both indoor and outdoor. And we observed what you see in this graph here is the error simply in the step detection, so not just the step counting by these different sensors. And as you can see, we have error that can be up to 40% sometimes. And the other thing that we did here was to ask our individuals also to walk at very slow speed in order to mimic what could be a patient condition. And we then took the best of these sensors, which was actually giving us acceptable results, and we tested it using the same approach in more controlled conditions on a group of patients with multiple sclerosis. What you see in this graph is the error projected as a function of the walking speed, And it's pretty evident that if we have a patient that is walking below I would say below 0.5 meters per second, we should just not give them these sensors. And otherwise, whatever we get as a result is just a random number. So before giving one of these monitors to our patient, we should really double check them in the lab. So to conclude this talk, I hope that I convince you about the fact that the technology is there. We are almost there, or at least we'll soon be able to measure everything we need, both for our modeling and for our monitoring purposes. But I think that we really should wonder whether we are good enough at the moment in using this information, or if there is something that we can do better. With this, I would like, on behalf of Laurence as well, I would like to thank our students, postdocs, and colleagues in Sheffield and Lyon, who of course did most of the work that we presented today as usual. Our funding bodies. I would also like personally thank Professor Capozzo for everything he taught me so far. And of course, thank you for listening.